Hello, there are an estimated 1.4 million below the elbow amputees in developing countries. Active prosthetics, or in other words, robotic hands, currently available on the market can charge upwards of $10,000. That's why over the past year, I've set about creating an active prosthetic for real-time muscle signal interpretation for a low cost. The prototype I've developed utilizes three main functions. The first thing is a surface electromyography sensor, or SEMG sensor. The next thing is an AI classification system built on top of that. And the third thing is a kinematic and control system. Electromyography is primarily used as a diagnostic tool in medical procedures. It gives you a way to detect the speed and the strength of a signal between 2 points. In a surface electromyography sensor, these points exist on the surface of human skin. In addition, there is also typically a reference point that acts on a bony part of the body. Where there is signal, there is a potential difference. Although this signal typically is a very noisy signal that exists in the micro to millivolt range, a microcontroller is used to measure this signal. But to get that signal in a form that is useful to the microcontroller, it needs to typically be between 0 and 5 volts. Subsequently, I developed an electromyography sensor that could amplify the signal from micro to millivolt range into the voltage range, in addition to introducing additional filtering steps to remove the noisy aspects of the signal. The input signal from the human skin is also an AC signal, which means that an additional rectification stage has to be utilized because microcontrollers can't deal with negative voltages predictably. The electromyography sensor I developed utilizes operational amplifiers to achieve this amplification, filtration, and rectification. Typically, 2 9-volt batteries would have to be utilized for this process. In order to reduce waste and hardware costs, I moved that system over to 1 battery, and I achieved this utilizing a voltage follower. The electromyography sensor I developed proved to work really well. In this, a user is tensing their arm. This is actually a fist gesture. As you can see, there is a clear voltage spike when the fist gesture is detected, and most importantly, as the fist gesture is held, the waveform continues. Eventually, the user stops tensing and the voltage spike goes back to a rest level. The reason this is desirable behavior is for part 2 of this overview, the artificial intelligence classification model. With those signals we've generated, we can classify them to distinguish what sort of gesture is being made. In the scope of this project, I collected data for 3 separate gestures: a fist, scissors, and paper gesture. I selected a neural network to distinguish my gestures from one another, and more importantly, I used a random forest classifier, which used decision trees. For example, a decision tree might look a little something like this. The algorithm evaluates a feature and then applies a rule to these features. Depending on what rule is followed, it moves further down the decision tree until it arrives at a leaf node. A leaf node is an outcome. In this case, an outcome is a gesture. That means that if you follow down a specific path, you'll get to a specific gesture. Once the algorithm has decided what type of gesture is being made, we can then send that to the robotic hand itself. This is a demonstration on a basic prototype I developed before I actually started this work. The mechanical design of this prototype was very poor, which is why the ring finger isn't responding. This is due to the lack of any kinematics or control, as well as poor mechanical pulley design. However, it does demonstrate the EMG and classification system working just as intended. Since I knew those parts of the project were now completed and working as intended, I was able to move onto the kinematics and control section. I conducted an investigation into the geometrical and time-based properties for a single digit, being the index finger. I achieved this using Denefit-Hartenberg's algorithm. The fingers of the computer-aided design are formed in 3 parts: a low, a middle, and a top section. Each of these sections has different link lengths. By recognizing that there was a maximum rotation of 50 degrees between each of these segments, the Denefit-Hartenberg algorithm could be utilized to map the position of the finger in reference to each of those sections and the palm. For example, this represents 50 degrees or 0.87 rads, and here is 0 degrees or 0 rads. Now that information about the angle position had been computed, I was able to map this to a current value by considering the current that the motor was drawing. As the motor spins in one direction, it pulls a string. This string acts on the finger, bringing the finger down in the process. As the finger starts to approach the palm, the motor has to work harder and harder and harder. This means that it draws an increased current. By considering that current value in real time, we can map the position using our kinematics we derived earlier and that current reading. This in turn allows us to move each digit individually to a specific angle of our choice. Using a form of proportional control, we can then move and stop the motor as we please as according to this angle value, giving us an accurate representation of the position of the finger and an accurate way to find that position in real time over many iterations. With the conclusion of the kinematic and control section, that's the three major aims covered. Future work will involve integrating this into a further developed prototype that has a better mechanical design and therefore can act more consistently. Thank you very much for watching. I look forward to taking this idea further.